Hello, welcome back, and today we're going to be going over April 10th classwork. And so the question at hand is, when there is a car at the top of this hill that's 10 meters in height, and it goes down and it hits this spring, what happens? And so there's three different things, or multiple different things that the question asks. And so the data that we have been given is the weight of the car. That's 13,000 newtons. And if you just do F equals mg and you divide 13,000 by 9.81, you should get around 1,326 kilograms. And the spring constant has also been given to us towards 1.0 times 10 to the power of 6 newtons over meters. And so that's what we have. And so for the first part, we're supposed to find the speed of the car as it's off this ramp, and then also how much this K is compressed. And so what we know is that in this system, energy is conserved. We're assuming there is no friction and air resistance. And so if we know that E final, let's say from here to here, E final, or the E initial equals E final, that's in this position right here, since it's at the very top and it's not moving, it's full of potential energy. Whereas at this moment right here, as it's moving, it's all kinetic energy. And so for potential energy, we know that's mgh, and kinetic energy equals 1/2 mv squared. And by looking at this, we could just cancel out two masses. So we should get 9.81 times 10 equals 1/2 v squared. V equals 2.1. And so that's your velocity, and that should go out to around 14 meters per second. And so that's the velocity and what it asks for us right here as it leaves the ramp. But now we're supposed to find how much this spring has been compressed. And so we can both use the potential and kinetic energy to compare it with the spring potential energy, which we know to be around, or which we know the formula to be 1/2 kx squared. So let's just do the kinetic energy since we found the velocity. We'll do the K, or 1/2 mv squared equals 1/2, and we know that the spring potential energy formula is 1/2 kx squared, x being the displacement of the spring. And so 1/2, 1,326.53, velocity squared, it'd be 14 squared equals 1/2, k being 1.0 times 10 to the power of 6, x squared, x, you cancel out the halves because they're both on each side, and then you should just get the mass. So it's velocity squared over the spring constant. And so when you calculate it and put it in your calculator, you should get around 0.51 meters. And this is knowing the conservation of energy, knowing that in this system, because we're not assuming that there's going to be any external forces acting upon it, that it's going to equal one another. And so from the potential energy to the kinetic energy, and then to the kinetic energy to the spring potential energy to find this displacement, that's what we have. And so you could also use mgh and compare that to the spring potential energy, but since we found the velocity, we might as well compare the kinetic energy with the spring potential energy. And so that's part A of this question. Now part B is, what would be the acceleration as the car hits the spring? And so let's put part B, I think here. Hopefully you guys can see it. Now part B, what do we know about the force? And so the force is negative kx. And so when we have this, we think to ourselves, okay, F net equals ma, and the force equals negative kx. Well, we have our x, we have our k, we have our mass. We can use this and set them equal to each other, where ma equals negative kx, and find the acceleration. And so that's what we can do right here, where we go a equals negative kx over m over 326.5. You should get around negative 384.46 meters per second squared. And so since we know that in this system F net equals ma, and then also of a spring the force equals negative kx, since the force is happening to the spring as the car is hitting it, we can find, and by setting them equal to each other, isolating A. And then lastly, honestly the easiest question of them all, if instead of the spring being compressed 0.5 meters, if it was instead compressed 0.3, what would then be the work of the spring? And so, or energy of the spring or work of the spring? I don't know, we'll see. And so, I think, assuming that it's a difference in energy, and if it's not, then work. I'm gonna be on the assumption that the difference in work, if it's not, then I'll otherwise let you guys know on the YouTube video. But under the assumption that it is work, we're gonna find the difference where with the 0.5 what the energy is minus what the energy is with 0.3 meters. So that would just be 1/2 kx squared minus squared, but this would be with 0.51, and then this would be with 0.3. And so this difference comes out to 85,000 joules. And so if instead it was compressed to 0.3 instead of 0.51, what would be the difference in energy, or what would be the difference in work done? And so that's what we have for today, or for April 10th, 2025. I hope you guys took away something, learned something. If I made a mistake, or if anything, please feel free to let me know. Thank you.